All right, welcome back. The next topic deals with something called trigonometric identities. These are like formulas involving the trigonometric ratios. So let's take a look at the different identities and what we can do with them. Trigonometric identities. You've probably seen all the tissue boxes over there against the wall, and if you take a closer look at them, some of that's going to make sense now. Those are all different trigonometric identities. During the next chapter, during chapter 7, there's a whole bunch more identities that we have to know. And I don't expect you to memorize them all, so you'll be able to write all of the identities on the tissue box and then use the tissue box during the test. But for this test, for chapter 6, there are certain identities that you need to know. So let's take a look at some of the basic identities. First, the reciprocal identities. These ones I think we already know. Things like the sine of any angle is the same thing as 1 over the cosecant of the angle. The cosine of any angle is 1 over the secant of any angle. The tangent of any angle is 1 over the cotangent of any angle. The cotangent of any angle is 1 over the tangent. In fact, we saw this trick. If we wanted to find the cotangent of an angle, we don't have a cotangent button on our calculator. We can do 1 over tangent. The secant of any angle is 1 over cosine, and the cosecant of any angle is 1 over the sine. So if we had to find the cosecant of some angle, on the calculator I could do 1 over the sine of that angle. These are the reciprocal identities, and we should know these. The next set are called the quotient identities. There's 2 of these. The quotient identities. Tangent is really the same thing as sine over cosine. And cotangent, if we think about the reciprocal identity, is just 1 over that. So cotangent is really just cosine over the sine. The next is the Pythagorean identities. There's 3 of these. First, Pythagorean identity is the sine squared of an angle plus the cosine squared of an angle is equal to 1. Now, before I explore the other ones, I want to look at this sine squared. What's going on here? What's being squared? Now, this is sine of an angle squared plus cosine of an angle squared equals 1. If I attach the square to the function, then it's the whole thing being squared. Now, there's a difference between the sine of an angle being squared and the sine of an angle squared. So this is not sine of theta squared. This is the sine of theta squared. Okay, so we're going to take the sine of that and then square it. Plus the cosine of the same angle squared is always equal to 1. That's my first identity. The next one is tangent squared of an angle plus 1 is equal to the secant squared of that angle. And then finally, 1 plus the cotangent squared of any angle is the same thing as the cosecant squared of the angle. These identities become very useful when we're simplifying and working with trig expressions and equations and solving and simplifying. Before we move on, I want to take a closer look at some of these, and I just want to go through the process of confirming an identity. Confirming identities are a skill that we'll see a lot in the next chapter, and it's really we're just trying to prove that something is true. So for example, if I wanted to confirm the identity that the sine over the cosine of any angle is really the same thing as the tangent of that angle. So I want to confirm this. I want to prove that that's true. If I take a look at a triangle, a right triangle, and here's my angle, my theta, and I've got the opposite side, the adjacent side, and the hypotenuse, I know that sine of the angle is really opposite over hypotenuse. The cosine is adjacent over hypotenuse. So the sine of the angle is the expression opposite over hypotenuse. The cosine is adjacent over hypotenuse. If I simplify this expression, change dividing to multiplying, opposite over hypotenuse times hypotenuse over adjacent, we can see that the hypotenuses cancel, and I get opposite over adjacent, which is indeed tangent. So I've proven it. I've taken this side and I've worked on it to show that it really is the same as the other side. Let's take a look at confirming another identity. Let's confirm the identity that the sine squared of an angle plus the cosine squared of the same angle is always equal to 1. Well, again, I'm going to think about my triangle here. And I've got my reference angle. I've got the opposite side and the adjacent side and the hypotenuse. And if I look at the sine is opposite over hypotenuse, so this is going to be opposite over hypotenuse squared. Cosine is adjacent over hypotenuse squared. So here I'm going to get opposite squared over hypotenuse squared plus adjacent squared over hypotenuse squared. They've got common denominators. I can combine them. Opposite squared plus adjacent squared over the hypotenuse squared. But opposite squared plus adjacent squared, what is that really? These are the legs of the right triangle. And we know that a squared plus b squared equals c squared. In other words, adjacent squared plus opposite squared equals hypotenuse squared because of Pythagorean theorem. This is really h squared over h squared. And again, that equals 1, no matter what the angle is. So here we have confirming trig identities, just plugging in the definitions and showing that they're always going to be true. Now let's take a look at two generic problems solving triangles, and then we'll look at two specific problems. In my first example, we just want to solve the triangle. When you see solve the triangle, it means you want to find all the missing sides and angles and anything that's missing here. So in my first example, I'm going to use a triangle, a right triangle, and I'm going to give you the following information. We're going to say that this is 23 degrees, and I'm going to say that this side is 11. So I can see that I've got a missing angle and two missing sides. Now, the missing angle, I'm going to call the angle here alpha. And I'm going to call the missing sides, I'm going to call them x and y. So we're going to find the missing angle alpha, the missing side x, and the missing side y. Let's do them one at a time here. First, the angle. Let's find alpha. I know the angles inside of a right triangle have to add up to 180. So 23 degrees plus the 90 degrees plus alpha is 180. Subtracting these from both sides, and I get alpha equals, here's my calculator, I'm going to do 180 degrees minus 23 minus 90. Alpha is 67 degrees. Now, finding the two sides. You might think Pythagorean theorem, but that's not going to help. a squared plus b squared equals c squared. X squared plus y squared equals 11 squared. There's a lot of things that x and y could be. I need to find at least one of them, and I'm going to do it by using trigonometric ratios. I've got a reference angle of 23. I'm going to find x first. So let's find x. Well, my reference angle 23, x would be the opposite side, and I know the hypotenuse of 11. So I've got an angle, opposite, and hypotenuse. What trig identity uses an angle, opposite, and hypotenuse? Sine. This is a sine problem. Sine says that the sine of any angle is the ratio of the opposite side over the hypotenuse. Substituting in, the sine of 23 degrees, I know the angle, is x over 11. Multiply both sides by 11. 11 times the sine of 23 degrees equals x. 23 is not one of our nice, well-behaved angles. I'm going to have to do it on the calculator. And another issue here, whenever you're doing things on the calculator, check your mode. I need to be in degree mode. So I'm in radian right now. So I'm going to switch to degree mode. And then I'm just going to do 11 times the sine of 23 equals 4.298 equals x. Now if I want to find y, I'm going to do something very similar to this. So let's now find y. This time I've got the same degree, 23 degrees. I've got the adjacent side and the hypotenuse. Now I know x. I suppose I could use Pythagorean theorem. X, which is the 4.298 squared, plus y squared equals 11 squared, but I'm going to use the trig. I've got an angle, I want the adjacent, and I know hypotenuse. What uses an angle, adjacent, and hypotenuse? Cosine. This is a cosine problem. The cosine ratio says the cosine of any angle is the ratio of the adjacent side over the hypotenuse. Substituting in, I get the cosine of 23 degrees is y over 11. Multiply both sides, I get 11 times the cosine of 23 equals y. I know that I'm in degree mode here, so 11 times the cosine of 23 equals, and it's 10.125-ish, somewhere around there. So solve the triangle means find all the missing angles and all the missing sides. Let's do another one, but this time I'll slow it down and I'll give you a little chance to do some of the work, to look at the trig ratios, to find the different angles and the missing sides. Let's do another sample problem. Solve the triangle. And here's the triangle that I need to solve, that I want to solve. And in this triangle, I'm going to tell you that this side is 5, and this side is 18. So what things are missing? What do we need to know? Well, I need to know this side right here. I'm going to call it x, and I don't know anything about either of these angles. I'm going to call them alpha and beta. Now, can I solve for alpha or beta first? Yes, because I've got this side and the hypotenuse here, but it might be easiest to solve for x first. Could I use Pythagorean theorem, a squared plus b squared equals c squared? Well, I know two of them. I need the other one. So yeah, I could use Pythagorean theorem here. So let's solve for x first. And the formula that I'm going to use is Pythagorean theorem. I could use, well, no, I couldn't use trig yet because I don't know either of those angles. I'd have to find one of those angles here. But the Pythagorean theorem says a squared plus b squared equals c squared. Substituting in, the a and the b are the legs. X squared plus 5 squared equals 18 squared. X squared plus 25 equals 18 squared, which is 324. X squared equals the square root of 324. Oops, I forgot to subtract I need to subtract the 25 first, don't I? So let's see, 324 minus 25, there we go. X squared equals 299. X equals the square root of 299, whatever that is. Shift square root 299. It's approximately 17.29. So now let's find the different angles here. Next, let's solve for alpha. So let's find alpha. I know this angle, and I know the opposite side and the hypotenuse. What ratio uses angle, opposite, and hypotenuse? This is sine. This is a sine problem. Start by writing down my identity. The sine of any angle is the ratio of the opposite side over the hypotenuse. Substituting in, the sine of alpha is 5 over 18. So what angle has a sine of 5/18? I'm going to ask the calculator that. And how I'm going to do that is inverse operations. So what we're going to do here is I'm going to take the inverse sine of both sides. That's going to look like this. The inverse sine of the sine of alpha equals the inverse sine of 5/18. Inverse and sine cancel each other out. Alpha is going to equal, and I want my angle in degrees. I know I'm already in degree mode. So inverse sine is second sine. See, I get the sine to the -1, inverse sine, of 5/18. 5 divided by 18. And we're asking the angle. We're asking the calculator, what angle has a sine of 5/18? And it told me 16.12-ish degrees. I know it's in degree because we were in degree mode. So this inverse sine, what angle has a sine of 5/18? 16 degrees. We still have one more angle to find. So now let's find beta. I could use trig again. I've got an angle, adjacent, and hypotenuse. This could be a cosine problem. The cosine of beta equals 5 over 18. But I also, now that I know alpha, this is a 90 degrees, alpha and beta have to be complementary. Alpha plus beta have to equal 90 degrees. And I know alpha. So 16.12 plus beta equals 90. Therefore, take 90, subtract 16.12 degrees, and it's about 73.88 degrees. So solving a triangle, finding all the different missing and interesting parts of a triangle. Now let's take a look at an application of this, a word problem dealing with this. So the actual work we're going to do is very similar, but the setup's going to be a little bit different. In the first case, I want to find the height of a building. And here's the scenario. I've got the ground level here. Here is my building. And I don't know how high it is. The building height that I don't know. But I know that if I am 310 feet away, at some point 310 feet away right here, so this distance is 310 feet. The height of the building, I don't know. I'm going to call that x. But I know if I'm 310 feet away and I look up to the top of the building, I can see the top of the building at an angle of elevation of 59 degrees. So 310 feet away at an angle of elevation looking up, there's my angle, 59 degrees, I can see the top of the building. So do you see the model here? I've got a triangle here. If I just pull out just the triangle model, the right triangle, I've got x, 310, and 59 degrees. So I look at this, I only want to know this side right here, which represents the height of the building. Pythagorean theorem won't help, I don't know the hypotenuse. But I know an angle and adjacent, and I want opposite. What trig function uses an angle, adjacent, and opposite? Tangent. This is a tangent problem. Write the tangent identity down. The tangent of any angle is the ratio of the opposite side over the adjacent. Substituting into my identity, the tangent of, I know the angle, 59 degrees, is equal to the opposite side, I don't know that, over 310. Multiply both sides by 310. 310 times the tangent of 59 degrees equals x. Back to the calculator, 310 times the tangent of 59. X, the building height, is 515.93-ish. So my final answer is 515.93 feet. Now this is a word problem, so make sure you answer the question, use the units. Don't just circle x equals 515.93. That really doesn't mean anything. Find the height of the building. The height of the building is 515.93 feet. All right, one more. Suppose an aeroplane is coming in for a landing. So I've got, here's the ground, and here's my aeroplane. And it's coming in for landing. It wants to land on the runway, and here's the runway. It wants to land on that runway. Now, right now, the plane is flying at an elevation of, let's say, 2,000 feet above the ground. 2,000 feet above the ground. And I know that the distance from where it is, the horizontal distance from where it is to the beginning of the runway, let's say, is 16,000 feet. So the question is, if the airplane wants to land on the end of the runway, what should be its angle of depression? What should it be? What angle should it be pointing down at? If the angle's too big, it's going to land in front of the runway, which is very bad. And if the angle's too small, it'll land past the runway, which is equally bad. So what does this angle have to be? All right, so do you see the triangular model here? Let's pull all this information out and take a look at just the triangle. And I know that it's 16,000 and 2,000. And I'm going to find this angle right here. I'm going to call it alpha. Here's my right angle. And then when I know alpha, I can find the angle that I'm interested in by taking 90 minus alpha. So I want to find that angle. Let's find the angle alpha. I look at it and I ask myself, what do I have? I want to find an angle. I know opposite and adjacent. What uses an angle, opposite and adjacent? This is a tangent problem. Start by writing down my identity. The tangent of any angle is opposite over adjacent. Substituting in, the tangent of alpha is 16,000 over 2,000, which I can reduce that to 8. The tangent of alpha equals 8. What angle has a tangent of 8? This is where we have to do the inverse tangent. So I'm going to take the inverse tangent of the tangent of alpha equals the inverse tangent of 8. Inverse tangent and tangent cancel each other out, and I get alpha equals the inverse tangent of 8. So on my calculator, I'm going to go to second tangent, inverse tangent of 8 equals, and it tells me 82.87 degrees. Now remember, that's the angle that's in here, not the angle that I really wanted. This angle here is 82.7. How do I find the angle that I want? It's going to be 90 minus that. 90 minus 82.87 is going to be 7.13 degrees. So the pilot needs to aim the airplane down at 7.13 degrees, and he'll land right at the end of the runway. All right, ladies and gentlemen, that's our last lesson for the week. It's Friday. Have a nice weekend. I'm kind of hoping that I'm going to be back starting on Monday. If everything went really well, I should be back. Worst case scenario, we'll continue video lessons next week. I am prepared for that, but I'm really hoping to be back on Monday. Hope to see you soon. Get working on the homework, and I'll talk to you again soon.